going to talk about the CID experiments at the Mont Terri rock laboratory, modeling of laser and reactive transport through concrete and Opalinus Clay. Mont Terri Rock Lab is an underground rock laboratory. This is in Switzerland, in northwest of Switzerland. You can see here in this small map. And this is in this laboratory, they perform many different types of experiments to investigate the properties of a clay formation, the Opalinus Clay, which is the formation where the Swiss are going to build their repository for radioactive waste. Not here, in a different place, but in the same platform. This experiment, CID, basically was designed to study the transport, special transport property, in this case, tritium, that is water, and chloride, an isotope of radioactive isotope of chloride here, chloride 36, through concrete and Opalinus Clay from a small point source like circulation interval in a concrete field. Okay, so in this drawing here, you can see this vertical borehole. Basically, they have different materials, different types of cements, bentonite. In the middle here in yellow, it's a concrete. It's a concrete made with ordinary Portland cement. The bottom is another type of cement. This was the CI experiment, designed to study what happens at the interfaces between these different types of materials used in the repository. But the CID experiment actually was designed to study tracer transport through these materials. So they drill this other borehole, this approach borehole, and then a smaller one. And you circulate tracers to a small interval inside the concrete. And the idea is to see how this is transported through the concrete and eventually through the interface between the concrete and the clay. So the vertical borehole, the BCI6, and the different materials were replaced in 2007. But the tracer transport experiment started much later. So this was really later on, and then the circulation of synthetic high pH solution started in 2018, and actually tracers were added in May 2019, so 12 years after the concrete was replaced in contact with the clay. The idea is to see the transport of the tracers and investigate if there has been clogging, for instance, between the concrete and the clay with the chemical reaction. This is a view of the experiment. Here on the left, this is Urs Meder, which is pretty much in charge of the experiment, and the cabinet where you have the tank with the circulation system, with the water and the tracers sitting on a balance, so you can monitor if there's any gain or loss of water, and the pump system, and line measurements for pH, conductivity, and so on, monitoring. Here on the right, you see a view of the experimental side. So this is you see the cabinet here. Then you see these metal plates. So under this plate, exactly the experimental borehole, the VCI6. So you have the concrete in contact with the clay. And then this large plate over here, where people are sitting on, standing on, is the approach borehole. Approach borehole goes at a 45-degree angle, following the bedding, parallel to the bedding, which is at a 45-degree, and intersects this other borehole, which is vertical. And then that's where the tracers are circulating. This is the setup of the experiment. So again, it corresponds to the picture. You could only see the surface. So you have the large borehole with the concrete. And then you have this other inclined borehole at 45 degrees, which is parallel to the bedding. And then you have a small, so this is all puckered off. And the only part that is open is this tip here, only 8 centimeters long. And that's where the tracers are circulated. So tracers by diffusion move from the circulation water here to the concrete and eventually to the Opalinus. So you can see here on the right, you see actually this circulation interval is not in the center of the borehole. So it's close to one side, which means that you cannot assume any type of symmetry in the system. So you have to do up to 3D modeling if you want to capture the geometry right. Otherwise, there's no symmetry that you can take advantage. So you have to do a 3D model. So here we have a first preliminary, purely predictive model. 3D model was using the punch load code. This is the setup of the experiment on the left, and on the right, what was implemented. So the model domain is kind of this box. We have the cylinder in the center, which is the concrete part of the borehole. Then only the injection interval is taken. So the rest of the work comes at an angle. It's not included in the model simplicity. And it's just basically the circulation interval, the tip of that borehole. And the dimensions, this is a cube, and each side is 5.52 centimeters. One face is closed, so one face has very small porosity and diffusion coefficient to simulate the fact that you only have the end of that borehole and pull particles from the borehole, simulating that. And then what is taken into account is the full volume of water in the circulation system. This is connected through lines to the circulation system when you have a volume 1.65 liters of water, so this is taken into account. 3D model, we have about close to 700,000 numerical elements. This is a finite difference model, integrated finite difference elements. So all these numerical elements are kind of small shoebox. Right, so the parameters for the model, basically, very importantly, the concrete, I mean, all the specifications and the dosage of this concrete. So the dosage was this amount of cement, 238 kilograms per cubic meter, and this amount of water, 190. So the water to cement ratio, which is an important parameter, is about 0.8. The rest, a large amount of aggregate, basically sand and gravel. So from this water cement ratio, then there's a study by Colin Walker, 2016, actually looked at the literature, many studies, and linking the water cement ratio for Portland cements to measure porosities and measure diffusion coefficients in the laboratory for tritium and fluoride, which actually came up with this relationship. So porosity we observed was a linear function of water to cement ratio, this number. And then the effective diffusion coefficients for tritium, for fluoride, but also functions of this porosity, which is not linear anymore and of large extent. You have also errors, like plus minus. There's a range up to the value. So with this, we get values, we can estimate values for the porosity, the diffusion coefficients. For the cement paste, but we don't have cement paste, we have concrete. So we have cement plus aggregate, plus sand and gravel. So basically, I multiply both porosity and diffusion coefficients by a factor, which is actually basically the ratio between the volume of cement and the volume of concrete, which I estimate using the weight proportions and densities of cement, water, and the aggregate. So then we get to go from these values to the same values, but to the concrete, not from the cement. The model calculation, basically what we have is pure transport purely by diffusion, but we take into account potential sorption, assuming linear sorption again. In fluoride, we have some sorption basically, and use a KV value for that. And at this stage, only isotropic diffusion. In the clay, we know that diffusion should be anisotropic. So this diffusion parallel to Venning is faster than perpendicular to Venning by a factor of around 4. That has been measured. But with this model, cannot be taken into account. So at this point, only isotropic diffusion in the clay. The concrete is isotropic. That is not the problem. Okay, so also concerning sorption parameters for both tritium and fluoride, so there were batch sorption experiments performed, and actually, I circled the values. This is for the concrete CID experiment on concrete for tritium, and also for fluoride 36, and the values basically are about 0.1, 0.13 potential sorption for tritium, and there's a range of values, but the large value which corresponds to the large chloride concentration that we have in the pool of water of 0.1 Clay is also 0.08. So actually, the number I take for both is 0.1. And these two numbers are very close to 0.1. So I take 0.1 liter per kilogram, which is the same as 10 to the minus 4 cubic meter. So this is the value I'm going to consider in principle for these calculations. Also, for the Opalinus Clay, basically, I take some standard values from previous studies, and these are values for tracer diffusion coefficients for both treating and chloride. In principle, I mean, they don't sort in clay. So effective diffusion coefficients, porosities, and the apparent diffusion coefficient. Apparent diffusion coefficient in this case is the ratio between effective and porosity, which gives you transport distance. So, okay, so that's the parameters. Again, these are now at this stage is purely primitive calculations. So I'll go. So I have all these plots. So these are for treating after 3 years of diffusion. I mean, from those equations that I had before, and I go back. From these equations to calculate the diffusion coefficients, I have plus minus range. So I consider a central case and a maximum porosity diffusion coefficient case and a minimum porosity diffusion coefficient case based on this equation. So the central case, this is I have left, center, and right. I have a horizontal section, XY, and 2 vertical sections, XZ and YZ. And on the dashed line represents the contact between the concrete and the clay. So you can see the tracer plume, how it expands on the XY, on the horizontal axis, and then on the vertical axis. You see that the interval is off-center. You see how the diffusion moves, the tracer goes to the concrete and eventually to the clay. And then it is the same for large porosity, large diffusion coefficient case, and small porosity, small diffusion coefficient. Extension of tracer plume depends on those. If I include sorption, so that can be 10 to the minus 4 millimeter per kilogram, then of course, that tracer plume is a bit smaller. It still calculates central, maximum, and minimum, but it's smaller. Chloride has smaller diffusion coefficients to begin with due to ion exclusion issues. So even without sorption, central case, we don't see much transfer into the Opalinus Clay. So it's mostly in the concrete, of course, in the large porosity, large diffusion coefficient, there's more transfer into the Opalinus Clay. In the small porosity, small diffusion coefficient, does not reach the concrete. And this is the same, including sorption. So even less transport. So these were purely predictive calculations. And these are what is being monitored at this point is how the concentrations of the tracers change in the circulation system in the water. So these are the predictions of how the concentrations for tritium and chloride go down. So central cases and for the maximum transport, maximum porosity diffusion coefficient, minimum porosity diffusion coefficient. In blue, the case without sorption, and in the red, the cases with sorption. You see that sorption with these values is not very strong. So the cases with and without sorption are very similar. And at this point, we access some first measurements. So some first measurements for both tritium and chloride. So you see here, on the left, tritium is this red line, not really HTO. So actually not so different from the prediction, but actually the model underestimates the activity, suggesting that probably we need a relatively smaller diffusion coefficient. So I mean, this curve should go higher up, so probably need a relatively smaller diffusion coefficient, and perhaps also porosity. And here the same for the chloride on the right. Naturally, it's the other way around. So I need to increase either diffusion coefficient or very probably sorption, because the interesting thing is that the curve for chloride in blue goes below the curve for tritium in red. And actually, chloride has a smaller diffusion coefficient than tritium. So the fact that actually you have a stronger drop for chloride suggests that sorption is very important for chloride. So that's what you see from this.
So with the different types of light, there is
Yeah, I mean, for each case, for either chloride or lithium, the solid line is the central case. From those equations, I have my water to cement ratio. I can calculate porosity and a diffusion coefficient. But I have a plus minus associated with those equations. Those equations also give me a minus. Maximum porosity diffusion coefficient, minimum porosity diffusion coefficient. And red and blue is just either with sorption or without sorption. But sorption is not so strong. That's the different one. Actually, the prediction was not so far off. But what is interesting again is the fact that the measured blue line is below the measured red line. And actually, in principle, it should be the other way around. This what's telling us is that probably sorption is quite strong. Okay, so this was purely predictive calculations, and then in a second stage with another 3D model, but in this case using a different code, console with diffusing, which is a commercial code. And the idea was also to check the effect of anisotropic in the Opalinus Clay, the effect that diffusion one bend is faster than the other. With crunch, it's not easy to do that. With console, you can do that. So in each different part of the domain, you can specify the full 3D diffusion tensor, all the components. So you can, in each part of the domain, specify how diffusion goes. So in that case, it's easy to do that. So we'll have, here you have a mesh. And we also use a finite element code, and the meshing capabilities are quite good, so you can do more or less complicated geometry. So you have the central borehole, which is filled with concrete. You also have the smaller borehole coming at 45-degree angle, parallel to bedding, and here inside you would have the small circulation interval, the end of this borehole. But actually, the tracer solution is in contact with the concrete. Before I had 700,000 numerical elements, now I have about 2 million. But this runs even much faster than before. This is quite effective. It's quite surprising. So, this is the calibration. Before it was predictions. Now this is a calibration based on the measured concentrations in the circulation system. So, also the volume of water before it was 1.65, but it seems that they actually use 1.5. Volume is a bit smaller than before, and now I've done fitting. Basically, based on these measurements up to the relative concentrations, in this case for tritium, the small symbols, and then we have the lines. Here's a linear scale, time relative concentration. Here is a log linear scale, just to see that the early part of the curve. And I have two curves. So I have a dashed line, which is assuming that the clay is isotropic, and the red line assuming that the clay is anisotropic. Actually, there's no difference, just because there's not much, as you can see, there's not much transfer into the clay. It's mostly inside the concrete. So what happens in the clay, that's not happening. But anyway, the values I need to do this fit for the concrete, I have to reduce the diffusion coefficient. So in my central case before it was about 8 10 to the minus 11, I have to use 4 10 to the minus 11. So a bit smaller, so actually I move the curve, the model curve upwards. For Opalinus Clay, I didn't change the parameter. And then for the anisotropic, for the anisotropic model, for the dashed line here, diffusion perpendicular to bedding is 4 times smaller than parallel to bedding. This is known from previous measure. But again, this doesn't have an effect because there's not much diffusion in the way. And here, I mean, this is what's just to highlight the fact that we have this deviation after long. I mean, the curve, we have a perfectly nice diffusion curve, and after 500 days or so, we see a deviation. I think this is expected to be an effect of an influx of water, actually. I think there's a pattern that actually is not so tight, so there's a little bit of water going into the interval along that pattern. So that is probably because of that deviation. Again, and we increase and then increase. Okay, these are the sections, the same sections as before. On top of the upper row, we have for the model with anisotropic diffusion in the clay, and the bottom row, isotropic diffusion in the clay. X, so the horizontal section and the two vertical sections. You can see a trace of the concrete clay interface and also the inclined borehole. If you really look from close distance, you see that actually in the isotropic clay case, you can see that the bloom actually after the concrete part, so after these lines, actually goes parallel to the vent, goes along this 45-degree angle in this case. So it goes like this. While in this case, actually, the bloom is kind of a balloon, a spherical balloon, because diffusion is isotropic, is the same in all direction. And in this case, you can see actually the effects of the effective anisotropic. The bloom elongates kind of this direction. But there is not much. Diffusion into the clay at this point in time is not that large. And this is the same for chloride. So again, same story. And then we are fitting based on the measured concentration in the circulation system. And in this case, to do that, I had to compare to my central case in the predictive calculations, I had to increase sorption. So increase the KD was 10 to the minus 4. Now it's 3.5 10 to the minus 4. This causes the curve to go down. Increase sorption in the concrete. Same parameters for the Opalinus Clay. And again, assuming here isotropic diffusion, right? An isotropic diffusion in the clay. That's what kind of thing. You see there's this deviation again after 500 days, but it is not so obvious as it was in the case of treatment. Probably related to this sorbing behavior of chloride in the concrete. And these are the sections. Again, as you see, there's basically all transfer is basically inside the concrete. There's a little bit into the clay, but not very much. It's mostly all in that. Right. So this is what we have, or what I have so far for the CIV. So it's still ongoing. So the tracer transfer experiment, but another component of this experimental package is the interaction between the clay and the concrete. Before the start of the experiment, we had concrete in contact with clay for more than 10 years. So one thing to investigate, which I thought part of the CI experiment is now, to investigate this interaction, what happens at this contact during this time. So for that we need a modeling study. In this case, it's not just transport, but we have reactive transport. We have chemical reactions in the model as well. The setup will be such like this. We have the central borehole filled with concrete inside the Opalinus Clay. Given this geometry, we can do a 1D domain with symmetry around the borehole axis. Again, now we don't have this. This is before the setup of the tracer transfer experiment. Now there is no inline borehole and circulation interval. This is before this was installed. So we have just the concrete. So 1D radial is enough. And as for the concept of the experiment, so we have again a reaction for all the cement phases and for all the secondary minerals, alteration minerals. Fast kinetics are assumed, so local equilibrium. But reaction kinetics are taken into account for the primary minerals in the Opalinus Clay, and also for the aggregate in the concrete actually, and calcite, sand and gravel. We use reaction rate loss from the literature and geometric surface areas calculated according to the grain size. Another thing is that in this model, one simplification is that we assume that the cement is fully hydrated since T0. Of course, with the concrete, it takes some time to hydrate and harden. So there's a 1 to 2 month period after the reaction is going on while the cement cures. So this is not taken into account. It might have influenced the earlier evolution of the system. But in the model, we assume fully hydrated cement is the main. Okay, these are the compositions of both the concrete and the Opalinus Clay from basically literature. And concrete, you have basically the cement faces and calcium silicate. These are volume fractions. If you multiply by 100, 100%. Calcium silicate hydrate, formaldehyde, which are the main faces, ethylene, carbonate, and these two calcite and quartz, which have 31% volume fraction each. These are the aggregate, the sand, and the rubber in the concrete. So the porosity, the porosity is the same as in my transport calculation. So the scale, so the porosity is the same, 0.38, same as in the transport calculation. Then again, assuming an initial diffusion coefficient the same as in my transport calculation. With reaction, this changes. There's a linear relationship between porosity and diffusion coefficient. Porosity increases, diffusion coefficient increases, and it goes down. The Opalinus Clay, again, based on literature, basically we have mainly clays, kaolinite, zeolite, and a little fluorite, and then some smaller amounts of microcline, outside dolomite quartz. And then there is a very small inert fraction, 2% in volume, which corresponds to the small amounts of siderite and pyrite, so an iron carbonate and an iron sulfide, which are not explicitly taken into account. So iron was not included in the system for some reason. But the volume that these phases take, it's taken into account. But iron is not taken into account. Again, porosity adds up to 15%, which is the same as in the transport. And diffusion coefficient 4.1 to the minus. Right, so again, this is basically another important component is the initial pore water composition, again, basically from literature and also due to available constraints and calculate. So we have different components, concrete and Opalinus Clay pore water. The Opalinus Clay pore water basically is very much dominated by sodium and chloride, so it's close to seawater composition. Sodium and chloride, no, it's interdiluted seawater composition. And smaller amounts of calcium and magnesium and sulfate. pH of 7.5. And then the concrete, basically it's a composition at equilibrium with all the cement bases. The composition at equilibrium with Poland and now I think like CSH. Importantly, very high pH for the one thing. Feature that cement would want the high pH, 63. Basically, due initially to very high, in this case, potassium concentration. So you have a very large difference in pH between the concrete pore water and Opalinus Clay pore water. Very strongly. Also, initial Opalinus Clay pore water is super saturated with respect to several of the minerals. But these spaces, then in the model, are not allowed to precipitate. They can dissolve, and some of them will, as you see, due to the interaction with cement and water, but they are not allowed to precipitate as not boost. So as the system does not start reacting on its own. So otherwise you would have reaction just without contact with the concrete. So these are not allowed. And we use the thermodynamic database from the code, supplemented with data for the cement phases from other databases. And then another final ingredient, which is quite important in the clay, is the exchange, the cation exchange, sorption by the cation exchange. This is well known since a number of years. We use the multi-site cation exchange model, initially by graduating variant, and then it's been slightly modified afterwards. And we use a cation exchange capacity of 115 kilograms per kilogram of solid, which is specific for the Opalinus Clay at this particular place, at this particular experiment. And here you have the reactions. You get the different types of sites, the 3H site, the reactive sites, and the planar sites. And basically, we have only sodium and potassium exchange in these first two sites. And then you also have sodium, potassium, calcium, magnesium, and strontium interacting in the planar sites, which are the sites that have a larger capacity. Most of the sites are planar sites. They have smaller amounts of time fluid and 3H sites. Right, so that's all the parameters in the model. Moving on with your databases and input files, and then you run it. If you're lucky, the program runs and you get some results. So these are results for porosity. So basically, I'm just focusing on a narrow region. This is just 5 centimeters. And you have the interface between the concrete and the Opalinus Clay, marked in red. So you have the evolution of porosity at 1, 2, 5, and 10 years. When you look at the concrete side, basically you see this front red, green, purple, blue. It's the dissolution of formaldehyde, very reactive phase. So this reaction front is moving, so we have increase in porosity, and then we get this second blip here, the second increase in porosity, which is associated with the dissolution of the CSH, the calcium silicate hydride, that starts dissolving once formaldehyde has dissolved. So after formaldehyde has dissolved in this region, CSH starts dissolving. And actually linked to that, the specification of cash, which is not money, but it's a calcium aluminum silicate hydride. So it's similar type of phase that incorporates aluminum. So the solution of this one is coupled to precipitation. So yeah, take of aluminum. But that actually causes a further increase in porosity. If you look at the Opalinus Clay, of the Opalinus Clay side, again you see a gradual decrease in porosity. And actually what we have so far as samples collected a few years ago, which were 5 years old. So samples were collected corresponding to the purple. Samples which were 5 years old. And these observations showed only a small change in porosity, which is consistent with the observations. You see a decrease in porosity, but it's not so dramatic compared with the initial porosity. So we have later on, so now we should expect a much larger change in porosity. 5 years, change in porosity was small. Okay, so that in principle, qualitatively okay. We reproduce that with just this predictive model. This is just a calculated evolution of pH. So here you see here to the left, concrete, here to the right, Opalinus Clay. So we started at 13 point something, then basically we diffuse the alkalis into the Opalinus Clay, so pH goes down, and then it's very stable after 2 years or 3 years at 12.8. And actually, this is being measured. So in the CID experiment, when now later on you have monitoring of the solution, this 12.8 is the value that is measured. So actually, this model matches very well with the pH that is measured in the CID experiment. And of course, on the Opalinus Clay side, the pH. I mean, you have a very slow increasing pH, like once you have all the buffering capacity into chemical reactions, and also transfer is very slow in diffusion. So increasing with the pH, but actually have a very large diffusion. For water composition, there's too many. Don't worry about that. This is for water concentrations at different times, 1, 2, 5, and 10. You see that there's a large gradient always between the concrete and the rock to the right, so different times. But I added a tracer. This is added in the model only. I added a tracer in the concrete at the initial concentration of 10 to the minus 3 mole per liter, just to see how conservative transport works in the model. So basically, you see that it be purely conservative transport, not affected by reaction. After 1 year, so this tracer was initially in the concrete, but not in the rock. So you see how this new tracer goes into the rock. So after 5 years or after 10 years, you have tracer transport affecting something like 1 to 2 meters distance. And actually, you see that all the other components, the alteration is much slower because of physical chemical reaction. And the fact that you have diffusion from the Opalinus Clay side of this tracer is not present in the rock. So the affectation is actually quite limited for all the other components, few tens of centimeters. The time exchange, again, on the top 5 years, on the bottom 10 years, I'll put just focus on the top. So you have concentrations, the different components in the different types of sites. On the left, basically, you see the potassium displacing the sodium from the planar side and displacing the magnesium, which is kind of the big line here from bottom side. It also displays the calcium. Since you have a lot of calcium in the concrete, actually you have extra calcium from concrete, so actually you're recovering that. On the right, we have the concentration scale is much smaller with respect to the -1, just to see the freightage side, actually, same thing, potassium displacing sodium. You see the little bit of strontium affecting also the water side. With time, I mean, this is kind of relaxing, little by little going back to normal values because basically potassium and sodium jump. When it's displacing everything else, mostly you only have a limited amount of it. It's only in the pore water, so you only diffuse a very finite amount into the clay. And actually once this is lost, then there's no more sodium and potassium. So little by little, you get this effect is recovering. So things are going more or less back to normal, and this amount of sodium and potassium diffuse into the volumes. So things recover gradually. And so the value exchange. Now, mineral reaction. So again, many lines, don't worry. Volume fractions. Top left, volume percent versus distance is 16 centimeters, 22 centimeters, 26 centimeters is an interface. And we see, what do we see? This kind of light blue line, the solution of formaldehyde. So we have dissolved formaldehyde in about 1 centimeter from the interface after 5 years. A little bit of dissolution of CSH and precipitated this other dark blue phase, which is cash, the calcium aluminum silicate hydride. So, which precipitates not only the concrete but also on the rock side. So 5 years and 10 years, and this other bluish line. That's the reservoir, that's a crystalline CSH phase. And then you see, for instance, on precipitation of calcite on the rock, and then some minor dissolution of quartz, and some minor phases. Importantly, if you go now to the right, so we have a much smaller vertical scale, only up to 2%. Importantly, you see this orange line albite, and so albite completely close to the interface, 1.5 centimeters, but also dolomite. Dolomite is dissolving. Dolomite is a calcium magnesium carbonate, and we have the magnesium mainly from the dolomite was in the precipitation of magnesium phase. Hydrotalcite and this MSH. CSH was a calcium silicate hydride, MSH is a magnesium silicate hydride. So we see the 5 years and changes a little bit after 10 years, but we have results for 5 years. So we can in terms of reaction rates, which is also kind of illustrative, I mean, we have reaction rate versus distance. Reaction rates, negative numbers means dissolving, that's a mineral that is dissolving. Positive numbers means precipitation, something that's precipitated. So here, the 5 years, we see very clearly, for instance, it's formaldehyde, valide. This is the formaldehyde dissolution. Formaldehyde from the cement compound is dissolving. And it's retreating, you see, 5 years, 10 years. This will what will be. And here we have this purple line of the dissolution of the CSH, coupled to the precipitation of the calcium aluminum silicate hydride. It's basically an uptake of aluminum. And then you see these also still at 10 years, all the rates and from down. You look on the rock side, many lines, don't worry. Basically, you see some dissolution of quartz, some dissolution of kaolinite. This provides silica, provide aluminum for the precipitation of calcium aluminum silicate hydride, the verborite. We have some dissolution of calcite, so dark blue, that causes this red line with the precipitation of monocarbon aluminum. But very interesting, this red line here is dolomite. So we have this dolomite reaction from dolomite is dissolving. So releasing calcium, releasing magnesium, releasing carbonate, and this is used for the precipitation of calcite and the precipitation of this magnesium silicate carbonate, this orange line. And actually, maybe you can see that the MSH that had precipitated previously at earlier times So just a little bit closer to the interface is now dissolving and causing the precipitation of another magnesium phase, this hydrotalc. Why is this important? If you look at just the calculated weight proportion of the different components, one interesting issue that was not understood is the presence of this magnesium maximum. This is again 16 centimeters, 22 centimeters, the interface weight percent. Magnesium, then we have this peak here. This was observed experimentally. I think I moved. Yeah. This is a SEM-EDX image mapping magnesium. People could see this enrichment in magnesium on the rock side, but not right at the interface. It's kind of why people we didn't understand why that happened. Actually, now I think it's clear in the model, but this is not quite clear. But we have this at the reaction front, the dolomite is dissolving, causing this precipitation of the secondary phases at that causing this magnesium other features is this calcium depleted zone. This is the complete. This calcium depleted zone, basically the solution of boron and enriched in carbonate. That was also observed, and this is also predicted by the model. And the model also shows a sulfate-rich zone, which is also observed. But having said that, I mean, the thickness of this is thicker than is actually observed. I mean, the observed measurement is much narrower, maybe half of length. Also, the position of the magnesium maximum should be a bit closer to the interface. So qualitatively, we reproduce it, but it should be at about 1 centimeter or maybe a bit less. And the sulfate-rich zone should be thicker. This is very narrow, but the interface actually should be thick. So qualitatively, we can reproduce that. Details, fine details, we cannot really get with this model. It seems that we are overestimating this distance, from the peak to the interface, and also the thickness of this zone. So what I tried was to start with this is already shown the evidence for this magnesium maximum that couldn't be explained. And then this is the same calculation I showed you, but now I tried a calculation with an initial diffusion coefficient of 10 to the minus 11, so smaller, 4 times smaller, just in the Opalinus Clay side, or in both the Opalinus Clay and the. If I do it only in the Opalinus Clay side, I see that I get the porosity, a volume of porosity very quickly. So after basically 1 year, porosity is really long. Think with secondary minerals, so this is not what is observed in the observation. If I do both sides, Opalinus Clay, actually, yeah, I get a faster clogging of porosity, but still, not quite like in the observations, but not complete. And if I compare again these weight percent and proportions, basically the extensions with this model, we produce diffusion coefficient in both sides. So again, a better agreement. So a narrower zone, so here, which is better with observation, also a smaller distance between the magnesium maximum and the interface here, a bit better than before, and still I don't get the sulfate part quite right. So, yeah, we are more or less there. We don't match exactly all the details, but qualitatively we are more or less there. So, in conclusion, regarding tracer transport, so the first part of the talk, in principle, we see no effect of anisotropy on the evolution of concentration. So, anisotropy referring to anisotropic diffusion in the clay. So that does not have an effect on the evolution of concentrations in the circulation system, because basically there's no much tracer reaching the Opalinus Clay. It's mostly in the complete. So anything that happens in the clay doesn't have much effect in this type of concentration in the circulation system. Fitting of the model to borehole data shows the effect of sorption, 4.36. We suspect an influx of water starting from the tanks. Also, only small, if there is a potential clogging of porosity at the interface, as we see in the reactive transfer model, it has a very small effect on the evolution of tracer concentrations because there's not much diffusion reaching the Opalinus Clay. And actually, this was modeled explicitly, which I cannot show here. So for that part, for the Opalinus Clay part, we have to rely on an overpoint, taking samples after the end of the experiment. So after the end of the experiment, we used to take samples to complete and in the clay and measure the tracer distribution profile. And then we see if we see effect of anisotropy. I will have to wait until the end of the experiment. And for the reactive transfer part, so the CI experiment, clay complete interaction, so we put in conventional reactive transfer modeling, local equilibrium for cement phases and secondary phases, and kinetics of primary minerals in the rock, allows a good qualitative reproduction of the observation, meaning small changes in porosity up to 5 years, although the model predicts stronger change in porosity with time, we'll see. And also, interestingly, this magnesium maximum close to the interface, but not right at the interface in the Opalinus Clay, which has big puzzle. Now we see it's caused by the mineralogy of the secondary phases, this reaction from the dolomites, as you saw. Again, fine-tuning, really getting things perfectly right, may require more careful consideration of electric double layer effects on the clay side, so the effect of ion exclusion, diffuse double layers, the fact that anions and cations move differently, have to be taken into account explicitly to fine-tune the results. And also, another possible effect is that early oxidation in small amounts of pyrite in the Opalinus Clay. At the early stages, when you drill a hole, basically, you put air, you put oxygen into the rock, so that may have caused oxidation of pyrite, the production of sulfate, which will contribute to this observation of the sulfate-rich zone in the interface that can capture very well. So those effects can be very, very perfect. So, official thank you to Mont Terri Consortium for funding, and to the partner organizations supporting both the CI and the CIE experiments. That is NAGA from Switzerland, and from France, Obayashi and Deviate from Japan, SKCN and TAM from Belgium, NWO from Canada, NWS from the UK, Helmholtz from Germany, so quite a large number of partners. And thank you for your attention. Have any questions? Thank you.
Questions regarding slide number 6.
Number 6.
Yes, there is concrete, but then you are taking account that concrete is made by cement and aggregates.
Yeah.
But then you have porosity in the cement and porosity in the concrete.
Yes.
So,
yeah.
How does it work? Because if I understand well, this porosity in the cement is 4.59, but whatever plus.
This is the cement. This is the cement base.
Yes.
This is cement. Just purely the cement part. So I have to upscale. I have to remove the value of the cement. So I have to take into account that I have the cement plus the aggregate. So then comes this correction, this total part. So basically, this is all this term, this porosity or diffusion coefficient in the mortar, in the concrete value, in the cement multiplied by this factor. This factor is basically, this is the volume of cement and the volume of water divided by the volume of aggregate plus volume of cement plus volume of water. So we are calculating ratio volume of cement, volume of concrete. This is the ratio. Which is porosity of cement is basically volume of water per volume of cement base, right? So then I multiply by volume of cement base divided by volume of concrete. So then I get the porosity. The porosity for the
calculation is the first that you are taking account as the concrete.
Yes, and then I use this. And I use this one. And I do the same thing for the diffusion coefficient. I scale them the same. Again, purely a prediction, but this is taking into account. We go from cement. This is volume of cement divided by volume of concrete. So I take into account the porosity, of course. is more in the concrete than in the cement, just because there's a large amount that is works and
Then with this number, the porosity that you obtain, you are playing with the sensitivity analysis.
right. So
porosity.
yeah,
With this number, I mean, with this, I mean, the first porosity that you obtain, what's the value?
yeah. So that's the central
So
one.
it's
It's 0.13,
0.18. It's not 30.
0.14, 0.14. Central. 0.14.
Because this porosity is also the one that you are considering in the reference
Yes.
transfer model.
Yes. Yes.
Okay. And another question is cementation coefficient that you're using for the chloride and the treating species, basically. The previous slide, it's also in slide number 6. Cementation coefficient is phi up. It's 3 and
No, but this is but this is okay. Yeah, all right. This is the initial one. This is so basically what Colin Walker did was look at the literature, experiments, measurements of porosity in different cements, measurements of diffusion coefficient in different cements, and knowing the water to cement ratio, to calculate. There was a relationship between water and cement ratio and porosity. So that's the regression. And that's the regression for the diffusion coefficient. So basically, it depends on porosity because porosity depends on water cement ratio. Then in the model, there's a linear relation. In the model, that's not have to be, but in the model, the relationship between diffusion coefficient and porosity is linear.
you're not taking
No, this is just for the initial value. This is for the initial value. This is for the initial value. But the change of diffusion coefficient in the model, as minerals dissolve and precipitate, it's assuming linear. It's linear. It's the only easy way to do it. Assuming a linear relation. If the porosity increases, diffusion coefficient increases by the same factor. If it decreases by the same. But it may not be linear, but the model seems.
so in linear, and you reproduce the values, it's a good assumption. Reason.
Yeah, you get. I mean, quantitatively, yes. Yeah. I mean, you are not too far off. I mean, if you get the initial value about right, then yeah, you cannot be too much off. I mean, if the initial values are not right, and porosity goes down, diffusion coefficient also goes down. The error is not huge, but yeah, maybe not. But with the code, it's with this setup, it's difficult not to have it linear because you have to match porosities and diffusion coefficients for two different materials. So, the easy way to do this for the approach using this code is using linear relation.
Another slide. Slide 20, 21 or 22. Just you are only considering the CSH. You are only considering the.
No, these are the primary phases. No, I mean I didn't have the list of this.
So you have all these.
Yeah. I mean, yeah, these things.
Solid solution.
This is the primary phases. Yeah.
Permarite is the only one that they see that it's.
Yeah. The important one is the cache actually, but precipitates is the important phase is this. I mean, yeah, I didn't have the list. But the important phase is this one. This cache. Very special. Actually, you see, look at the rates. Yeah, we have the solution of the CSH actually is linked to the precipitation of the cache. I mean, even I also have the other CSHs with small constants, but the one that precipitates is this cache. It's the calcium aluminum. This has a calcium silica ratio of about 1, and it's an aluminum to silica ratio of 0.05. So it's a small calcium to silica ratio, which makes sense, but it incorporates aluminum, and it's faced with aluminum. That's
for casual, there's still one species.
I have 3 different ones.
3D.
This is the one.
So it's like 25 or so. That was a 3%. No, 34 perhaps. Yeah, this one. When we see the solution front of Portlandite, CSH, you see that has let's say, an intuitive shape. And then when we go to the reduction of porosity, basically the clay, Why do we have this oscillation?
Yeah, because there's many more phases. At least, I mean,
I don't have that minimum, but
In the-
causing that minimum.
that is impact. That is impact. Yeah, that's the impact. That minimum in the place is which I don't think is real. I mean,
Yeah, because, I mean,
in the model predicts that.
I mean, sulfate, right?
No, I mean, yeah, I mean, you get the sulfate, you do have, that's it. But I mean, in the concrete is very obvious. You get the Portland line is for 10 years, for 5 years. Portland line and CSH coupled with the division of fashion. It's kind of two main reactions. But for the clay, you have many things.
A question related to that, because maybe it has to do with discretization, and if you discretize more, to make smaller elements, then maybe you have discretization in one node.
No, this is, I mean, this is not just, no, I mean, here, more or less, you can more or less see that.
Sometimes you see,
Yeah, I mean, but this is not just one. Yeah, sure. Measure, you can see what you can see. But
I mean,
the porosity plot, I mean, this is not, I mean, this is, it's not just one node. I mean, these are, no, the stabilization is quite fine. I mean, it's, you can see maybe here, there's one point here, and there's another point here. Can you see that? It's, if you're going to a millimeter or something like that.
if you go to the following first, all the minimums, let's say. Yeah.
I mean, these all, I mean, these are,
As a SERP after 10 years, you see the
I know.
every time you see a peak. And this peak is
The biggest one, no, yeah, but I
one
mean,
node.
this biggest
What
one.
happens, that's my question, what happens to the peak if you reduce the element size by 2 points?
Yeah. I haven't tried that. I mean, there is an idea. Yeah.
Because,
But there is,
and here also the cache is also, there's a peak at one node.
it's just because, there is because this is very, very critical. You just dissolve right at the, where it starts, where it just starts. You said, a repeating in front. So it just basically dissolves at the very first point, because these are fast reactions. It dissolves at the very first point where the space is present, then it reaches equilibrium with that. And there's no further reaction. It only happens in the very first node where it happens, when it is present. There is no CSH here, there is no Portland.
But that gives you the peaks.
I mean, well, it is, but I mean, that's because there is, it's a very fast reaction. And it happens at the first occurrence of that minimum. And it equilibrates, and it's very fast. Yeah, you can see it here. In specification, you can see that's actually, this will be the Portland dike peak. Actually, you can see there's another point here where it actually, it's much smaller. The solution rate is already much smaller. Again, I mean, we are getting to the point, so this is already quite a fine specification.
About the results, you said the anisotropy doesn't affect that much because most of it is happening there.
Right. It does not mean that it's not important. It just, what I mean. Let me go. Treating a little bit more. Let's look at here. See, so concrete between these two lines, right? So most of the diffusion, most of the transport goes into the concrete. So there's a little bit going into the blade, but there's not that much. Actually, you see that the plume extends a little bit into the blade. But actually, it's the far end of the plume, so very small concentration. So the amount of mass that you've actually lost to the blade is quite small. So actually, the concentration at this stage, of course, if you wait maybe a long time, it will change. But at this stage, the changing in concentration in the borehole, in the circulation system, these calculated lines responds to the concrete, because most of the tracer mass is in concrete. There's a little mass in the fluid clay is very, very small. So this is this curve. I mean, basically, the conclusion is by looking at this, you cannot say what happens in the clay. I can say what happens in the concrete, but I can, by looking at this curve, I cannot really say what happens in the clay. There's no resolution. Maybe after a long time, maybe I could say something, but not at this.
Yeah, of course. You don't have data, you only have data from the.
Yeah, of course. Yeah. At the end of the experiment, you have overpouring, you have samples, you can measure the tracers in the clay, then we'll be able to say something. Sure, yeah, of course. But with this data, with this monitoring data, we can say, yeah, we can say something about the concrete, we can really say much about the clay.
Other.
So on solvent, the clay is strange.
No, I mean, for reactive transport, no. But for just pure tracer transport, yes. I mean, it's much better. For just pure. No, I think you can do some reactive transport modeling, but no, I mean, but in just for like more the flow and tracer transport, yeah, it's very good and very powerful, works very fast, it's very efficient. Yes. It's commercial boat as well. We have a license of this, so we can use it for free, but I mean, it's very, it runs very fast. It uses, actually, it's very smart. I don't know if the smart is the right word, but I mean, it detects what sort of a hardware you have. So it takes advantage of the processors you have. I can use my normal PC, but it says, oh, you have, 2 cores with 4 nodes in each core. So I'm using that for the calculation. So it kind of does a mini parallelization and it runs very fast. I mean, these calculations with crunch, which were smaller in terms of numerical, same type of calculation, but I have 700,000 elements, took about 20 minutes, my normal PC. The calculations with console, which have 3 times as many elements, really takes 6 minutes on the same machine.
How much the CPU?
6 minutes.
6 minutes in the other?
20.
20 minutes.
With 3 times less. No, because the crunch only uses 1 node. Purely CPU programming. Here also it sees the computer and says, oh, you have this one, part of the, so it does parallelize. So it uses all your processors. If you have more processors, it will use more. It adapts to what you have in your computer. I don't know how they do that. I mean, you can see when it's running, you look at your processors, oh, they're all chip away, they all run. If you use Splunk, there's only one running, the other one isn't doing.
It's the multi-processing. Are you finished? Okay. I thank you for coming.
Oh, thank you.
This install. Okay.
Thank you for coming.
Let me see whether there are many people in the.
Or maybe you have questions for someone.
Okay.
Okay. Thank you.
Bye-bye.